ก็ว่าถ้าใครเข้าเพิ่มคูณได้80%เราก็จะออกไปเชิญให้นะครับแต่ว่าเฉพาะเซสชั่นที่เป็นอะไรก็เอาไปไหนโดยตัวเอทูนะครับซึ่งเป็นเซสชั่นที่เป็นสีเทานะครับถ้าใครเข้า7 ใน 9นะครับก็จะไม่แตกให้เป็นสีขาวนะครับแล้วก็พรุ่งนี้นะครับเซสชั่นย้ายที่ห้องจำหน่ายนะครับซึ่งอยู่ตึก B2 อาจจะเดินงงๆนิดนึงนะครับคือเราจะมีก่อสร้างอยู่มันอยู่ข้างหลังตึกก่อสร้างนะครับเรียกว่าห้องจำหน่ายนะครับถ้าคนแบบนั้นก็อาจจะรู้จักว่าห้องนี้เป็นห้องประชุมนะครับก็พยายามเดินที่ตึก B2 ขึ้นไปชั้น 2ห้องจะโดดๆมุมนิดนึงเพราะห้องมันใหญ่ที่เท่าเลยนะครับอยู่ชั้น 2ตึก B2 นะครับก็คือเป็นชั้นวันเสาร์ประมาณนี้
ตัวป้ายชื่อที่มีกับงานมีคนมันต้องต่อเป็นคนที่จะเป็นคนพูดขึ้นก็โน้ตบุ๊กไม่นะมันน่าจะสลับอยู่นะเอ็ก
เห็นไม่ได้ไปไหนอ่ะแต่คนเขาไม่เขาจะใช้เครื่องเขามาเป็นขายที่เขาเพราะว่าจะเดี๋ยวเขาดูข้อมูลเขาเป็น
ก็ไอตัวของ IBM ที่พูดเมื่อวานเราได้ขอว่าใครเขาลงเราก็น่าจะอยู่ในนี้เดี๋ยวยังไงวันนี้เขาก็พูด3 นะครับที่ไหนที่ข้อมูลจะได้เอามาต่อท้ายOkay. Got it. Very fun. You're waiting for HTML.
오디오에 들어왔잖아요. But the audio is not working. Okay, it works. It works.
Good morning, everyone. So welcome again for some of you who were here yesterday already. We're going to wait a few more minutes because it is a Friday morning traffic, so there's a lot of people still coming in. But we'll be starting very shortly. So, as you notice already, we have some refreshment in the back. If you don't have some water, please feel free. Just grab a bottle first. And we'll be starting shortly.
No. Yeah, I understood the idea. So. I've tried. But I didn't want to come try it.
Okay, I guess as more people are coming in, we should get started. We might run a little bit past the scheduled time, but we still have a long break, so that should be no problem. So good morning again, and welcome to the Deep Learning AI Institute. So this is sponsored by the Asia Pacific Neural Society. It's a professional society which basically have many experts from all Asia Pacific regionals, but also from tour actually, so it's a real network area. And we encourage you to look more into society and also hopefully you will join us in some of the future activities and become a member as well. So here this morning we're fortunate to have Professor Soo-Young Lee from KAIST, Korea Advanced Institute of Science and Technology. So we'll be talking to you about deep learning. Well, I call it deep learning basics. So it's a little bit different pace than history talk from this talking about speculative neural AI aspect and also deep learning aspect. So today it's somewhat of a tutorial format, I believe, but you'll find out. Of course, if you have questions, then please be ready. We will ask, if you have questions you understand right away, you can put your hands up. But otherwise, you can ask questions in the session, or you can pass some papers around, you can write something down in case you want to ask some questions. Okay, so without much ado, we'll get started. Please,
Thank you, Jonathan.
and a big hand, please.
Thank you for the organizer to give me time to give something I like to talk. And actually, Jonathan asked me 3 different talks during this session, so I tried to add some basics. So what I mean by basics is actually root of the deep learning, or similar to our ancestors for myself. So where the deep learning came from. Actually, the deep learning tries to learn something from the data that's actually happening in our brain. So what I mean deep learning basic is how our brain actually do learning from the data, and then how the brain mechanism is related to the current deep learning algorithm. That's the main thing I'll talk about today. That actually means this is a very simplified diagram of human brain. Do you figure out how this 2-dimensional version of human brain came? They cut my head along my ear horizontally. That means you have left ear and right ear, and this front side. So the signal coming to our ear is going through all this red and green signal pathway and go to the auditory cortex, and then they go to the higher language area. So what I try to talk right now is how the signal coming to the cochlea goes through several different stages and then come up to the auditory cortex and higher language area. So this is actually the root of the deep learning that based on many layers, from the sensory part to the decision or feature extraction part. I also have, there are different pathways from the cochlea to the auditory cortex, what I call bottom-up pathway. And then we also have the other pathway coming from the auditory cortex to the cochlea. That's what I call top-down pathway. So these 2 pathways, bottom-up and top-down pathway, actually interact in our brain with certain good reason. Actually, the number of pathways from bottom-up is actually much less than the pathway from top to the bottom. So top to the bottom pathways is actually dominant, and why? What kind of role this will be done will be discussed tomorrow based on the top-down attention problem. So before I go on, I need to introduce what I mean by what is myself. And my name is Soo-Young Lee, and this is Chinese characters. Let's say this is life and forever. So my life is forever. And in other words, instead of 2 O here, just omit 1, then means so young. So I'm always young. That's the way I live forever. Okay? So this is the way I have your email. If you want to contact me, you may say this way. And KAIST, as Jonathan said, Korea Advanced Institute of Science and Technology. It is a special university in Korea. We started as a graduate school only. Then we acquired undergraduate in 1990, but we still have more graduate students than undergraduate students. For example, we have around 4,000 undergraduate students all in science and engineering, but the number of graduate students for master and PhD degrees is more than 7,000. And then all the students are supported by government, and we don't belong to Ministry of Education. We belong to Ministry of Science and Technology and Future something. That means we have some special status in Korea. And then I'm a professor of electrical engineering, but I also have director position of Institute for Artificial Intelligence and also director of Brain Science Research Center. So basically I'm trying to combine the brain science and then AI, basically deep learning or neural network areas. So that's the talk I'll do today. This was the talk we did, and there was a deep learning summer school. This one is deep learning winter school, but last year there is a deep learning summer school in Spain, and I was one of them to give lectures, but just the only reason I said here is the number of audience in this 1 week tutorial at Spain was more than 1,300 registered students. So that means a lot of people around the world, not only in Thailand or Southeast Asia, all around the world, many people are interested to learn more on the deep learning. Why we are interested in deep learning or AI? So we need to look for history, because the future is not just coming from nothing. The future is an extension from the past to the present. So to predict the future, you need to look for your past. So history is something interesting to you. And as far as I think, the starting point of AI coming to the Pygmalion and Galatea, have you heard about the Pygmalion before? You don't look for mythology in Greek. In Greek mythology, Pygmalion was an architecture, a sculptor, tried to make a nice woman statue based on limestone, and he was so amazed on his own output, so he asked God to let the statue become alive. Then the alive statue is called Galatea, and then you know the final story. They got married and lived happily forever. So that means even older days, even mythology ages, human always wanted to make something they work similar to their own. That's the starting point. And then current status of AI starting from pre-1990 or 1940s, they have HAPS and macros. They are pioneers on this learning, and Rosenblatt. But this time, between 1960 to 70, that's what we call dark age of the neural network. So in this area time, the so-called rule-based expert system dominated AI. But in the mid-1980s, the post-renaissance of the learning-based AI, neural network came. And then in the mid-2010s, we come up with the second renaissance, and everybody now say the learning-based system is the way we go for the AI. That's the thing we think about it. But so there are also confusion on the terminology. Some people talk about machine learning, some people talk about neural network. But for me, they are not much different, although some of the machine learning people don't care about where the algorithm came from. They just look for their efficiency, while the neural net people try to see the algorithm is somehow related to the brain. Everybody knows the AlphaGo, beat it, the top Go players before, so I skip this part mainly. But basically, again, the reason AlphaGo helped us a lot is how to show how we can win the best available and contribute to the solutions. And then basically the success recipe of the AlphaGo is try to combine strengths of human brain and computer. Either one, human brain alone or computer alone, may not be good enough. But if you combine these two different things, for example, the intuition or pattern recognition of human brain and also fast computing and huge memory of computer, these two different things. But if you combine them, then you can beat anything. That's the natural thing we do. That's what actually AlphaGo shows us. And then also, the current AI look always successful on image recognition and speech recognition and Go game. But what are the common factors of these success applications? They are basically very simple problems as far as human brain functions are concerned. Also the data, the input data of these systems are very structured. For example, image recognition, the images are very simply formatted as two-dimensional or two-dimension by the time pixels. Also for the speech, they also divide into time, frequency, the coordinate. So basically very simple format. As long as you know how the input looks like, you have very good start to think what's going on. However, now we are moving to higher cognitive functions, such as language understanding, knowledge development, situation awareness, decision making, and behavior. All this, what I call higher cognitive function, that actually means this image recognition, speech recognition are lower cognitive functions. So currently, everybody thinks deep learning becomes superior even against the human, but success on this higher cognitive function is still very limited, but that's the way we should go. So actually the conversational agent or chatbot I will discuss tomorrow will actually try to combine all this functionality to come out with a game. So now let's go to the basic thing, how the AI and brain science come together. This is the same. Many people working on so-called robot and humanoid robot, while I'm interested in the soul or the brain. So whatever robot body somebody make it, we can put the soul or brain on top of this one. And then you need to think what kind of functionality this brain or AI should have. And you always need to look for what's next. So if you look at the smartphone, everybody has a smartphone, but the success story of the smartphone has not been quite a long history. It's very short time, but it changed our life a lot. Then we can also look for how our society will be changed. So everybody thinks the phone is developed for transmitting the audio signals. Then they figure out if audio signal can be communicated, why not video data, why not the data, then they can figure out this smartphone can have memory and computing power, then they utilize it for the contact and schedules. How many telephone numbers do you remember for your family or friend? I used to remember more than 100 when I was young without my smartphone. But after I use my smartphone, maybe less than 10. Because I don't need to worry about that situation. That means my brain becomes worse than before. Not this way, not just simply memory function. Maybe my brain becomes worse than, but for other higher cognitive function, I think my brain becomes better than before. Well, another example is knowledge assistant, dictionary, translator, and navigator. So then what's next? So some of the simple brain functions now move to my smartphone. Then what's next? the remaining function we need to improve ourselves. But what's that thing? If you remember this movie, so-called Night Rider, or in the old TV series, and the autonomous vehicle, and then a detective or spy, I don't remember exactly, but they cooperate each other, and this autonomous vehicle is actually the symbol of the current autonomous driving cars. It can drive by itself, it can talk to human, and try to understand what's going on with these people, and he said, okay, also there are many people think the same way how the AI will change the future society. One example is Stanford AI report, and the other one is many people talk about. In that sense, we started a brain neuroinformatics research program from 1998 to 2008 to two different goals: try to understand brain information processing mechanism, and then try to utilize this mechanism to develop brain-like intelligence system. Basically, we try to understand what's going on in our brain, try to develop something like this. So this one is the slogan we have: by giving intelligence to machine, we like to provide freedom to mankind. That's what we did. And in this project, we have about participants from the 15 Korean universities around the world and 35 professors and grad students here. And these are the final output we demonstrated in 2008. Unfortunately, it's written in the language is Korean, but what happened to the sound? Can you hear the sound? So this system has 2 eyes and 2 ears, 1 mouth, and then communicate with the human, and it does all the things secretary are supposed to do, like to make the scheduling and keep their contact and turn on the music and turn off the music, and face recognition. You think this one is actually the most popular uses of current Amazon Echo or all the intelligent secretary or AI secretary currently working on. Turn on the music or turn off the music is actually the most people use with the Amazon Echo at this moment. But this one was done in 2008, 10 years before, even 3 years before Apple Siri 10. But unfortunately, this system was just demonstrated at lab. It couldn't go out to the real world. Why? The speech recognition quality was not that satisfactory. It worked with my student voice, but it cannot work for everybody. But after then, as you see, the deep learning come and many data and fast computer, they did to improve the speech recognition quality, and that solved the problem. But basically, everybody like to have this kind of thing, and that's the way we do. And then to do so, we have 4 brain functions: head image recognition, speech recognition, and learning and behavior. And then we'll try to come up with more higher cognitive functions again: knowledge, situation awareness, and decision making and action behavior. So I'll discuss how we can handle at least the situation awareness and the tolerance. Okay, that's the prerequisite. Now let's go to the main topic. That means the relationship between the current deep learning and brain science. And whenever you try to talk of neural net models, you need to talk these 3 different things. So neural models actually is the model of the neural network. Neural network actually means collection of many neurons. So to understand the neural network, okay, if you want to understand how the forest works, functions, then you need to understand some knowledge on each tree. Then how each trees are related to each other to form a forest. So to understand the neural network, you need to understand each neuron, and also you need to understand how neurons are connected to each other. The last one, also most important part, is how the learning functions are done in actual world. So these three things we need to work on it. So I talk about neural model because Nick already discussed the spiking neuron yesterday. But how these spiking neurons are related to biological neuron signal? That's usually coming from the integrate and fire neuron model. Actually, the integrate and fire neuron model coming from biological neuron. This is the simple diagram of the biological neuron, and they have many dendrites, and then they have an axon, and this axon is connected to another neuron through the synapse. That's probably what you learned from the biology session classes. But how the neuron actually create these spikes? As a function of time, as Nick said, the brain signal, neuron signal actually coming as a spikes. And then how these spikes actually generate in our neuron. And basically, the membrane between the neuron, so you have the neuron, and then inside the neuron and outside the neuron, they have potential differences because there are the different ions, so sodium, potassium, and chlorine ion, or many other ion concentration inside and outside of the neuron has different concentration. If we have more positive ion inside, then you have higher potential, right? So then if you have voltage differences between inside and outside, that affect the transmission property of the so-called ion channels inside and outside. This is inside and outside of the neuron. This is membrane, inside neuron, outside the neuron. The membrane has many holes. Along this hole, ion will move around. So the property of this ion passage is not a fixed property. It is changed as a function of membrane voltage between here and here, inside and outside. So the neuron spikes is coming as an output relationship between the ion concentration of inside and ion concentration of outside that affect the voltage difference between two membranes, and then this voltage difference also control the ion passage. So it come up with a positive feedback. For example, this is the regular or resting potential. And then for some reason, like sensory data or coming from other neuron, the positive ion concentration inside the neuron increase. It increased up to certain level, but it reached certain threshold voltage, then the property of ion channel got changed. The more ion is coming to the inside. So they open the ion channel, so more ion is coming to the inside, that means the potential is rapidly increasing up to certain level. But once it reaches certain level again, then the property of the ion channel also got reversed. So positive ion need to move outside to the membrane, so the potential rapidly drop down again, and then it reaches the resting potential again. So this is the basic mechanism how neurons create spikes. And the basic mechanism is the interaction between ion concentration and membrane potential. They are nonlinear, highly nonlinear. So it can suddenly increase the concentration and potential, then suddenly decrease the concentration. So that's the generate the neuron spikes. How these neuron spikes encode neural information. Okay, so before I go on, this model, neuron spike model, has been studied by Hoskin and Huxley long time ago, and they got Nobel Prize for it. Then it's very simple model, so just to have the membrane potential, the increase of the dVdt is the VM is membrane potential, so dVdt is the increase of the membrane potential coming from all the current injection, that's actually the ion concentration, and also potential difference in conductance. They model it and do experiment, come up with some mathematical model, and their mathematical model was successfully predict the neuron spikes. But that model is not easy to simulate in simple computer, although there are groups really working on this single spike generation for millions of the neurons. I'm not interested in that part. Excuse me. I'm interested in more general collective behavior of the neuron. So I need to simplify the Hoskin-Huxley model. So the simplified model called integrate and fire model, it is basically the same. The same basically means the membrane potential increase is coming from ion concentration from other regions. So basically, it has differential equation formulation, but it also says until it reaches certain threshold, if the ion concentration is coming, then the potential will be increased. But if it does not reach the threshold, then nothing happens. However, if it reaches the threshold, they create the spikes and coming to the rest potential again. So that's the same very, very simplified model of this neuron spike. So in which, until it reaches to the threshold level, it just follows the differential equation, so integration of the input signal. But when it reaches to the threshold, it creates spikes, and let's go to the rest potential again. Very simple thing. Then you need to see how these spikes are encoded into information we like to deal with. Basically, there are two different approaches. One approach says the number of spikes coming. The number of spikes coming for given time. So how many spikes are coming for 1 second? Provide the information of the signal intensity. So number of spikes related to the signal intensity. That's the I call the firing rate theory. The other group also interested in exactly when the time the spike is actually coming. That is more advanced theory, but it requires more calculation and more theory. That works for like sound localization in our ear. For example, if you have two eyes, that means your sound, when the sound is coming from certain direction, the distance from the source to my ear, left ear and right ear, have some time differences because the distance is different. So that small differences, time, can be utilized to identify which direction the sound is coming. So therefore, the time difference is also important. But current neural net model, majority of neural net model doesn't utilize the temporal information at this moment, and they just utilize the number of spikes as a signal strength. The majority of cases, and the other cases is what Dick said yesterday, they are working on spiking neuron later on. But today, I'm not worrying about that. I just say the important information is encoded in the number of spikes during the time. So how the number of spikes are related to the incoming signal, sensory signal. So you have more incoming signal is coming, then the membrane potential will increase more rapidly. So that means the spike duration becomes smaller, that means number of spikes during given time will increase. So this is the relationship between the incoming signal of the neuron and number of spikes based on this integrate and fire share. And then it will turn out like this curve. That means if the incoming signal is less than threshold, then nothing happens. But if it reaches above the threshold, the spike is start coming in like this form. Is it similar to something you know? The majority of CNN, convolutive neural network for deep learning, utilize so-called rectifier linear unit as a nonlinear function. This function looks like rectifier linear unit, although the threshold is somehow shifted. And also the critical point here is not actually linear, but how this turning out. If you have this one, this property is just for single neuron. But as you know, biological neurons always have noises. Biological signals have always noises. Or noises on the threshold lower level, noises on the input signal, noises of refractory period. There are all kinds of noise going on. So if you add on some noises on these parameters, and then this curve coming out something like this, smooth out curve. It becomes more similar to the rectifier linear unit many people are using at this moment. So this one, called rectifier linear curve, is basically coming from noisy version of this integrate and fire neuron. So that's the starting. However, if you're only looking at single neuron, then how you can calculate the number of spikes? That's not easy. So the way actually the single neuron we are looking at it is collective behavior of many neurons, many of the neuron spikes here. So you have many of nearby neurons, and also they have time averaging all certain durations. So the simple neuron model we are working on deep learning right now is not a model of single biological neuron. That is model of many biological neurons at nearby time. So they just have many of the similar property neurons, but they come up with different spiking time. Like if you have the number of spikes calculated in the set many of neurons and certain time, then you will see the curve like this. So that's the main thing I like to talk for neuron modeling. So the current neural model I have is it is coming as a summation from other neuron. Why it come up as summation? Because the input of the neuron is actually, I said, ion concentration from many different other neurons. So if there's one neuron and ion is coming from many different neurons here, then ion concentration on this specific neuron is naturally added up because ion concentration, number of ions is just adding up simply and weighted. So that's the simple model, and we have nonlinear function, and currently similar to the rectifier linear unit, or in the previous case we use hyperbolic tangent or sigmoid function. So basically nonlinear. So that's the main result we have. Any questions so far? So I went on very quickly, so if you don't understand, it's okay. But the only thing I said in this so far is the currently used neuron model on deep learning is coming from biological model of many similar neurons. Okay? Next thing is the network. How these neurons are connected to each other. That's the important part. And there are many possible ways you can look about it. The first one is so-called fully connected neuron. So that means one neuron connected to all the other neurons. That's basic assumption. How many neurons do we have in our brain? I cannot count exactly one by one, but roughly say 100 billion neurons exist in our brain. If 100 billion, one neuron is connected to 100 billion neurons, how many connections do we have? I don't know exactly how to pronounce it, right? So too many. It's also almost impossible to make in our simple brain. Therefore, we come up with different architecture. We don't use this fully connected method. We have so-called layered architecture. That means each neuron has different layers, and then there are connections between layers, but there's no connection inside the layer. That's what we think is coming from the biological neurons. Again, at the first figure I show you, in this figure, there is connection from here, 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 here. They are coming. So that means there's not much connection from here to auditory cortex directly. They are coming into many different layers. That's the starting of the layered architecture currently many people use. So the layered architecture is also very important for the engineering design. So sometimes I think the nature evolution is very good to come up with good biological design. And on the other hand, if we believe somebody created human, then creator is really good engineer to know what's going on in our world. So layered architecture is very important part. So from the input you have the output auditory cortex. For example, the auditory cases you have cochlear, inferior colliculus, and superior, all this going on this layered architecture. But also we have auditory and vision pathways are quite separate, at least at the early stage of data. Then how you can combine the auditory and vision processing is another thing you can talk about. So far I have neuron model, and I also said the network architecture is layered thing. That's the thing we did. And then we see how they are learned from the data. So we try to investigate how the features are extracted from this cochlear, the early stage of signal pathway, or in the cochlear or auditory pathway. And the same way is the early pathway on the visual from retina. They also come up with feature extractions. And then they go on higher, layer by layer to the higher cognitive areas. And then the first thing you see is for the auditory pathway in the cochlear, you know there are cochlear and there are many inner hair cells. The inner hair cell is actually transducer from the acoustic vibration to neuron signal. They have about 3,000 inner hair cells. Each of the 3,000 inner hair cells work as a band pass filters in frequency. So they can do that. And then after that, for inferior colliculus, they have time frequency representation of the acoustic signal can come up with many different features. So we can learn the features. And the same thing is in the visual pathway. For example, if you have two-dimensional pictures like this, the first low-level auditory, the visual pathway signal, they detect some edges, horizontal edges, vertical edges, etc. They edge in small area, they look at small area and is there any edges, horizontal, vertical, etc. But above that, then they combine the two different edges and coming in more and more area. So this hierarchical architecture in layer pathway also show the visual and auditory pathway are organized in layers, not the fully connected networks. Then the local features, we know how the edge detector is coming is very clear. So local features are extracted. But you know the deep learning started in so-called deep neural network, and recently majority of cases they use CNN, convolutive neural network. So what's the difference between DNA and CNN? So CNN is looking for the local area, of course. That's actually coming from biology in our brain. But I also have several other examples how our visual system go on convolutive feature extraction from the local area. Okay, so when you look at this picture, try to see the brightness between this area A and area B. What do you see? The intensity, brightness area A and area B, they are different, right? This is much darker and this is brighter. However, if you have some connections there, you will figure out the bright intensity of this A and B are actually the same. But if you look at here, this one looks much brighter than this. Why? Why that's happening? Because how do you perceive is not the actual brightness. How do you perceive is relative brightness. This point against the surrounding. So this pixel, this brick is surrounded by darker block. So we see this one is brighter. While this one is surrounded by brighter one, so we perceive this as a dark. So what you see is, how you see is, or how you perceive is not actually the signal there. We see the relative property. So relative property is related to the edges or the surrounding. That's one important thing. The feature extraction in the local area, we don't look for the whole image. We look for some local area and see whether this signal is brighter or darker than against the other. Okay, another example. You remember who he is? If you know his name, George W. Bush, the former president of the United States. How about this? Upside down version of this George W. Bush, right? However, I just turn it around of the right image. You feel some strange thing happen. See? This is actually upside down, so you see this is strange. Also, you see this eye looks strange. If you go back, you didn't see much problem on this image. But actually, if you look at carefully, this eye and this eye is basically the same thing. Or the mouse is the same thing. So when we look at this image, we don't look for the whole image initially. We look for the local features. So we look for the eye and mouth and nose. It looks like okay, right? Then you have the higher level, the lowest layer or the above the layer say they have eyes and mouth is okay. At the top, the higher layer say, okay, mouth is higher than eye. That means this face should be upside down. So you don't feel any strange faces in this here. So you understand it okay. But if you look at this figure, so you try to look at this face, this mouth looks strange. Also, eye looks strange. That's the reason. So, what is the explanation of this? This is to explain this phenomena. we also say, okay, we don't look for the whole image initially. We look for local features initially. So that way, looking at the local features, we have problem, difficulty to learn images. So this is the actually what convolutive neural networks are actually doing. They don't try to understand the whole image at the same time. They just look for local features at the low level, and then they combine the local features to come up with the actual image. Is it clear? The convolutive neural network we are using now has some biological background, at least a cognitive background, as you can see. Therefore, if you come up with the many deep learning architecture, they also say the eye cases, vision, you have retina, and also it goes to the visual cortex at the end. They have many different layers. In the early stage from retina and later on, they detect these local edge filters. And these local edge filters actually looking for the relative intensity of this line compared to the surrounding. And then they have some specific images of eye and ear, etc. And then they combine this for the whole face. That's the thing I want to talk. Another system you may be interested is so-called Jennifer Aniston cell. Do you know who Jennifer Aniston is? So there are some specific part of the neuron, even for the monkey, they respond to the face of the Jennifer Aniston. Jennifer Aniston only. It doesn't respond to any other, but it responds to the whole thing. That is the symptom when the whole image is recognized by certain neuron later on. But who started this convolutive neural network? Many people think convolutive neural network is invented by Jan LeCun. But Jan LeCun never said he invented CNN. Actually, Professor Fukushima in Japan is the first to come on this convolutive neural network, although his model did not incorporate the learning part of the feature extractor. He used some fixed amount of the feature extractor initially, but Fukushima was supposed to do it. And Jan LeCun was several years later, but he also said he didn't invent it, he discovered it, because the CNN is coming from biological model. It's not invention. All right? So feature extraction. The other part of learning. So learning usually involves so-called end-to-end learning right now. They start from all the sensory data as the input. The output is final decision as a classification. So how we learn from the sensory data to the classification. The first part is feature extraction. The next part is discriminant learning that try to see which class belong to which one. So that means the faces whether Jennifer Aniston or others. So that's what we call descriptive learning. And I think you all know the perceptron and multi-layer perceptron works well. So I skip this mathematics. But one thing is said, is it the multi-layer perceptron or multi-layer deep neural network can solve any classification problem? Is there any problem that cannot be solved by deep neural network? That's the main thing. If you know your algorithm network can solve any problem, then you are quite safe. And you can push all your effort to solve the problem because you are confident on the result. But if you don't know whether your algorithm can solve the problem or not, then you may hesitate. And if the result does not come out nicely, then you may want to go to the other way around. So whether you think this is solvable problem or not is very important. for your attitude. Also, the attitude greatly influences on your final performance. So it's very important to say the technology you are using, the multi-layer perceptron, can solve any classification problem is very important. And to do so, we talk about the performance of single-layer perceptron. That means you only have one layer. You only have input and output. Then how they can solve the problem. Then you can easily say it can solve only this kind of problem. That means there is one decision boundary can divide these two different groups. Then the single layer perceptron is solvable. It cannot solve this problem. It's called exclusive OR problem, as the Marvin Minsky and Pepper, the written for the disability or poor performance of the neural network. So but this exclusive OR problem can also be solved by two-layer perceptron. And if you have three-layer perceptron, basically it can solve any classification problem. Three-layer is good enough to solve any classification problem. Does it mean something to you? Then you may worry why current deep neural network researchers may use more than 3. Right now, some people using more than 100. More than 100 layers they are using. Why they are using more than 100 layers? Even though theory said only 3 layers is good enough. Any answer for that? Still many people try to answer that. I don't have exact or answer for this, but I can guess something. The way we recognize or classify the input, I borrowed from 30 years old book here. And what he said is, again, single layer perceptron come up with one decision boundary. So if you have 2 layers, input, hidden layer, outer layer, what it does is each of the hidden layer generate one decision boundary. So this neuron make this decision boundary, this one is another decision boundary. Then this exclusive OR problem can be solved by this one. In class A is belong to the upper side of this boundary and lower side of this boundary. So upper sound and lower sound is considered as an AND logic. So the last layer can do this AND logic operation. So if you have 2 layers, you can solve this problem. However, you cannot solve this problem again. So to solve this problem, you have again the first hidden layer make a decision boundary like this, and the second hidden neuron here, second hidden neuron at the second layer make AND operation of many this decision boundary. So you have this area come up with one area, and this one come up with another area. Then at the top layer, you say this and this are the same class. So then it come up as an OR operation. So one is high, then it's good enough. So this 3 layer can solve any classification problem. So this, again, the first hidden neuron create the one decision boundary, and then the second hidden neuron create AND operation of all this boundary. So come up with this one, and the last one come up with the OR operation of this space. So 3 layer is good enough to have any classification problem. Understandable? How this problem can be solved then? I didn't say clearly. So the way we solve this problem is we divide this black area into many of the area with this. So divide this one, etc. Then each one is makes like this one. And then each neuron here, second neuron at the second layer come up with one area. And then the last layer comes with as an OR operation. If one of the air conditions satisfied, that is the black area. So 3-layer perceptron can solve any classification problem, provided they have infinite number of decision boundaries. Because the area may be divided into many different areas, so each one come up with many different decision boundaries. So if the number of neurons at each layer can go to infinity, you can solve any classification problem. So 3 layers is good enough, but the penalty you need to pay is the infinite number of neurons for each class. But you know that's not good. If you have infinite number, you can never achieve it. And also if you increase the number of hidden neurons here, that increase the number of synapses, which actually need to be adaptively found from the training data. So if you have infinite number of hidden neurons, that means you need infinite number of training data. Otherwise, you cannot solve it. Okay, that's the reason I guess, that's the reason we need to have more layers with smaller number of neurons for each layer. That's what currently used deep learning researchers are looking at. So instead of 3 layers, and each layer has infinite number of neurons, what we use right now is you extend this one layer into many of the small layers, many layers with small number of neurons. That's one of the success of the current deep learning algorithm. And can you see why that's helped to the performance? Why instead of big one, single one, you have many of the high layers come up with better performance? That's a very good question you need to answer. Okay. Now we know the learning rule. This basically is error minimization. The learning is basically optimization problem. Try to find the proper connection, synaptic value or parameter to achieve the goal. So it's basically error minimization problem. So that can be done by calculating the gradient. So it's very simple. We don't use complicated optimization algorithm. We prefer the simplest word. We look for Occam's razor. That means the simplest is the best. You don't look for complicated algorithm. Why? Our brain cannot do that complicated algorithm because they come up with the simple neuron. The neural function is very limited. So you can have simple algorithm that works for all. That's basically gradient algorithm. And then you need to compare how this general purpose classifier is different from the other popular classifier. The other popular classifier is called Bayes classifier. Have you heard of the Bayes? It's a big statistic researchers who come up with nice theories in communication and statistical information theory. So Bayes classifier is a theoretically optimum classifier to classify the data into 2 parts. Like the data, one has this distribution, the other has this distribution. Then you can have optimum decision boundary and say below this level it is class A, above this one is class B. How to make the decision boundary, threshold value. The Bayes come up with formula for that, and that's based on optimization theory. Then how this Bayes classifier and deep neural network come up with differences. Which one is better or etc. The result is you cannot say which one is optimal, which one is better than the other in general. That depends on what kind of problem, what are the data characteristic of the training and test data. So perceptron try to divide, and this how I said is single layer perceptron, try to divide this blue and yellow region by for this linear decision bound. However, the base classifier can make decision in non-linear decision. That means instead of the single decision bound, they can have co-decision bound. That means it is more flexible. On the other hand, the perceptron come up with non-parametric, or while base classifier for on parametric. That means we assume certain probability distribution function of for the base field, usually Gaussian distribution function or Laplacian distribution function. And if you look at the Gaussian distribution function, you need only the mean and standard deviation to figure out everything. So instead of looking at all the distribution function, you need to look for only two parameters, that is mean and variance, that's what we call parametric. Also, the perceptron can run on online data, so for each problem, each training data, you can incrementally adjust the decision boundary. So these two are slightly different, and the advantage of this base theory is basically it can come up with non-linear decision boundary, while single layer perceptron can only have one line linear decision. That's big drawback. However, in other properties like the non-parametric and online adaptation is superior, better than the base field. Therefore, if we can overcome somehow the linear separability of the single layer perceptron, then your classifier works better than base classifier. How you can do that? That is multi-layer. So by incorporating multi-layer architecture of perceptron, you overcome this linearly separable problem while maintaining all this. Therefore, it works better than the base classifier standard. There are simple learning rules. I'll skip that part. You can find that learning rule in all kinds of literatures. And the remaining thing, I have only around 10 or 13 minutes. There are several issues. One you need to overcome, and actually that has been overcome by the deep learning of recent technology. One is called the good and poor generalization. So basically, we try to make optimization based on training data. But the test data is different from training data. For example, if you want to understand human voice, how long it took for you to learn to understand your mother's voice? How long did it take to learn language, your mother language? You cannot remember when you are young, right? But if you have children or grandchildren, you may know how long it takes to learn a baby. A baby learn how to understand the speeches. Usually 2 years plus minus several months. So it takes 2 years to learn speech, even with our human brain. But AI, deep learning, they are still the same thing. They need 2 years training data and 2 years of computing time if our brain and our AI software work similar efficiency. But as you may guess, the current deep learning algorithm is less efficient than human brain. So it should take more time and for the more data and more training time. How we can do that? That's actually coming from the current success of the mobile or internet communication provide more data and GPU provide more computing power again. So I skip this part, and basically more important issue is how-called generalization. That actually means even you learn something from your training data, the actual classification test or test cases, you see something different. So the important part is how you can come up with good performance for unseen data. Unseen data is very important part because, as you say, the rule-based system didn't work well for the unseen cases, while learning-based system work well for unseen data. So that's very important part. That's what I call generalization. In Korean, we usually say the good student understand 9 when they taught only 1. Do you have the same thing? If I teach you 1, you are supposed to understand 9 others. So that's what we call generalization. So to overcome that, we should say the network complexity and problem complexity should come up with good match. So what I mean by network complexity is basically roughly say number of adaptive elements. And then the problem complexity is actually how difficult to solve the problem, the classification problem. If they are matching well, the system will work well. If in this area, when the network complexity is bigger than the problem complexity, that means if you use too many synaptic weights for the simple problem, then you may not work well. So you try to come up with good generalization is very important part. And then there are several ways to overcome that problem. And the current success to overcome this generalization difficulty is called dropout. So that's one big successful of the listen to deep learning domain. So what I mean by dropout is basically suppose you have input and hidden layer and output. This is whole network. But when they are training this network, they randomly remove some of the hidden neurons. They randomly remove some of the hidden neuron and then train the network for the remaining only. For the next training example, they also randomly remove it. That means the removed neuron may be different from sample to sample. How kind of effect this dropout will affect? They provide some randomness on the training process that greatly overcome the generalization problem. So majority of current deep neural network, they utilize this dropout for the rest of the performance. And that's maybe related to the neuron model I discussed before. The single neuron model we are working on right now is not a model of single neuron. It is a model of many similar neurons. That means one neuron here is not necessarily a single neuron. It's maybe come up with a single neuron, and then they have nonlinear or randomness property on it. So that improves the generalization performance. The next trick, if you look at the winner of the many competitions, recognition competitions in the world right now, majority of cases, the high rank performance coming from so-called committee machine. Not the committee machine is basically, it has many classifiers, and then the final result coming based on the result of each of the classifiers. That's what I call it. Committee machine, or sometimes we call it ensemble average. The same as human being. And you want to make a big decision, how you do that? You organize a committee of people and let each people make decision and like a voting, and then the final decision coming from the committee. That is very robust way of the decision making. But the problem of this committee meeting is how you recruit the committee members. Suppose you want to have a committee, then you have 100 committee members. How you collect your committee? How you invite the committee members? we don't look for committee members with the same personality or same decision making. If 2 or 3 members have the same property, personality, and they always come up with same decision, they are not useful anymore. Only one is enough. Because the other guy always come up with the same decision, so it's not useful anymore. Therefore, to make this committee machine work well, you need to come up with different property or the committee, each of committee members, and then make final decision. How you can come up with different property of this machine, coming from different classifier and different data, different network architecture, different learning process, etc. And then let's say what's next. So far I just tried to explain some of the basic property of deep learning, especially CNN, then how the CNN are related to some information processing in our auditory and visual processing. And the next thing we'll talk tomorrow and the day after tomorrow, maybe try to go on more on these examples on the emotion recognition part for the chatbot on tomorrow, and the day after tomorrow I'll talk on more on the brain internal state. It is also more scientific part, but in the future that will work for the human. So nobody wants dumb machine-like AI. People want human-like AI. The human likeness includes the brain internal state. I mean, it should have emotion, it should have personality, it should have some consciousness in it. So how you can give this personality into AI? That's the last talk we'll discuss. Thank you. Any question?
Actually, it's really excellent talk. There's a lot of detail. I think I was looking at the audience, some of them a bit confused because they might not have the machine learning or AI background much. So, because we're running out of time, so what I suggest we could do, we will take a short break because the next session starts at 10:45. So, Professor Lee will be here actually next 2 days as well. So there's lots of time over a break, over lunch, and also next 2 days if you have questions to ask. Just before we take a break, just make a quick announcement. Actually, we're very honored to have experts from neural area, Professor Lee, also Professor Kasaba, talking about give talks yesterday. I'd like to announce that actually we're very honored to have them collaborating with the School of Information Technology at KUTT. So we're actually in the process of signing MOU. So our students will be able to actually collaborate and work with them. So we renewed an agreement with Professor Kasaba. We're signing a new agreement with Price and Professor Lee as well. So this is good news for the KUTT, mostly SIT students. So anyways, so we'll see you come back at 10:45. Please feel free to come up to Professor Lee or also Professor Kasaba and ask the questions.
Yeah, thank you. I will be here anyway. So.